Have you ever thought about how we could possibly take the intuitive, visual expertise of a seasoned farmer, someone who spent decades just looking at crops, and transfer that exact knowledge right into a machine learning algorithm? How do you actually teach a computer to look at a leaf and know exactly what's wrong with it?
Well, let's dive right into it. Welcome to this explainer, where we're going to decode the rigorous and honestly fascinating data preparation process that makes AI-driven crop disease detection possible. We hear about AI doing incredible things all the time, right? But the secret sauce isn't always the algorithm itself. Actually, it's the meticulously prepared data that feeds it.
Here's our roadmap for today. We're going to cover the plant disease problem, move from the orchard to the image, dive into the pre-processing pipeline, explore teaching machines to see, and finally, look at the real-world impact. Let's get to it.
Section 1. The plant disease problem. So, why does all this actually matter? Well, agriculture is basically the backbone of human survival, but it is under constant threat. Take mangoes, for instance. They yield a massive 50 million metric tons globally, but fungal and bacterial diseases can absolutely decimate entire crops if they aren't caught early. And the real challenge here is how we perceive this problem versus how a computer sees it. To us, a human farmer can easily spot those dark necrotic patches of anthracosis spreading along the edges of a sick leaf compared to a healthy one. But in AI, it literally just sees a grid of numbers and pixels. For the machine to tell the difference between a healthy leaf and a sick one, it desperately needs structured, reliable pixel patterns.
All right, Section 2, from orchard to image. Let's talk about capturing that data.
Capturing those distinctive pixel patterns actually starts out in the muddy, unpredictable physical world. To build a solid AI, you first have to hunt down the data right at the source. The researchers building the Mango Leaf BD dataset followed a really systematic workflow for this. They didn't just casually scrape photos off the internet. No way. They consulted actual agricultural experts to study the diseases, carefully selected 4 different orchards across Bangladesh just to make sure they had enough variety, and then physically went out to hunt down infected leaves right before winter to meticulously photograph them. It is an incredibly labor-intensive process.
And here is what that raw image acquisition actually looks like. The researchers captured thousands of these images using a standard 12-megapixel smartphone camera. Notice the plain white background? They physically placed the leaves on a white table right out there in the orchard, trying their best to isolate the leaf's features. But, even with the plain background, raw images are just messy. The lighting varies, the scale isn't uniform, there might literally be dust on the leaf. If you were to feed this raw image directly into an AI, the algorithm is going to get super confused.
Which brings us to Section 3, the pre-processing pipeline. This is the absolutely crucial bridge to our AI models.
To build an effective plant disease detection model, researchers rely heavily on something called data augmentation. Now, models can very easily overfit to their training data. Basically, they just memorize specific photos rather than actually learning the underlying disease patterns. So, by introducing controlled distortions to the original images, researchers artificially expand the dataset. This forces the model to generalize and become much more resilient when it faces brand new, unseen data.
Let's break down exactly what happens to an image during this pre-processing phase. First off, every single image is resized to a standardized dimension, something like 240 by 320 pixels. Then, the images are manually cleaned up and cropped to completely remove background noise. Finally, they go through augmentations like zooming, rotational tweaks, and shear transformations. But you might be wondering, why go through all this trouble just to change the pictures? Well, it all comes back to human versus machine vision. If a photo of a leaf has a little bit of soil or sky in the background, your human brain instantly ignores it, right? You know it's not part of the leaf. But a machine learning model, it might look at a brown patch of soil in the corner and mistakenly think that soil is a symptom of a leaf disease. By carefully cropping out all that background noise, we force the AI to concentrate solely on the biological traits of the plant itself.
Now, think about those rotational augmentations we just mentioned. As a quick mental exercise, why on earth would a data scientist intentionally take a perfectly good photo of a diseased leaf and flip it 90 degrees or turn it completely upside down?
Because the real world is chaotic. When this AI is eventually deployed as a mobile app, a farmer standing out in a field isn't going to have a perfect white table set up. The wind will be blowing, the leaf will be at a weird angle, and the smartphone camera itself might be tilted. Rotational augmentations and shear transformations artificially simulate these crazy perspective shifts during training. It essentially teaches the machine to recognize the distinct disease pattern absolutely no matter what angle it's looking from.
Moving on to Section 4, teaching machines to see.
and preventing AI bias.
Take a look at this distribution from the MangoLeaf BD dataset. After all that pre-processing, the researchers ensured there were exactly 500 images for every single category. And this is absolutely vital. Think about it. If an AI sees 2,000 images of anthracnose, but only 50 images of bacterial canker, it's going to develop a massive statistical bias. It'll just start guessing anthracnose for everything, because statistically it's a safer bet. A perfectly balanced dataset ensures the AI gives equal, undivided attention to every single disease.
And because the data is standardized, clean, and perfectly balanced, the AI can finally lock onto the unique traits of each disease. Take this leaf, for example. This is damage from the cutting weevil. I mean, it looks exactly like someone took a pair of scissors to the edges of the leaf, doesn't it? Because the AI isn't distracted by background noise or confused by weird angles anymore, it can mathematically map the exact geometry of these scissor-like cuts and correctly diagnose the pest. It's a real game changer.
And finally, Section 5, the real-world impact. This is all about democratizing agriculture.
All of this meticulous work, the background cropping, the rotations, the strict balancing, it's all about moving powerful diagnostics directly into the hands of everyday farmers. As the creators of this dataset beautifully noted, the true benefit of machine learning really isn't fully harnessed yet for social goods like healthcare and agriculture. By building, pre-processing, and then freely publishing a standard dataset of mango diseases, researchers are actively democratizing precision agriculture. They're laying down the groundwork so that any developer, anywhere in the world, can build a mobile app that helps a local farmer save their livelihood.
The magic here isn't just in the AI algorithm itself. It's in how we translate the raw chaos of nature into structured data that a computer can actually understand. So I want to leave you with this thought. If carefully cropped, rotated, and balanced images can teach a smartphone to diagnose a mango tree, what other incredibly complex global problems are just waiting for the right data set to be solved? Thank you so much for exploring this explainer with me today. Keep asking those big questions, and let's keep learning.